How reliable are stand stocking estimates, a comparative analysis on current and new methodologies? Two speakers in this one, I believe. Keith, is that right? Where are you? Yep, okay. Keith Hatchula has been a professor at Confederation College since 2011, teaches courses in natural resource management, wildlife management, and introductory and advanced GIS to a variety of programs. He has over 20 years of experience in forestry with an emphasis on wood supply analysis, inventory data analysis, modeling, auditing, and the assessment of sustainability. He received his BSc in Environmental Sciences from Guelph and his MSc from Lakehead. He maintains consulting and research interests in related technologies such as remote sensing, LiDAR, and unmanned aerial vehicles. With Keith today will be Dr. Julie Lee. He's a remote sensing research scientist currently working for FP Innovation in Montreal. He's been there since 2016. He obtained his master's degree in geomatic engineering in China in 2008 and his PhD in Earth and Space Science at York in 2013. His PhD research was focused on individual tree-based species identification using LiDAR and multispectral remote sensing data. In the following years, he's had an insert industrial postdoctoral fellowship and worked for KBM Resources Group to further develop the single tree-based automatic LiDAR approach for improving enhanced forest resource inventory attributes. His current research focuses on the use of mobile and portable LiDAR systems for automatic STEM attribute mapping, and as well the development of operational tools for provincial forest regeneration and post-harvest log waste assessment using drone technology. And so Keith and Dr. Lee, you're at it, guys.
So we're going to have a little bit of a similar theme to Doug's presentation, I think. So this is fortuitous that we're going after him here. But other than Doug looked at a number of variables, and our study is going to be focused at looking at stocking estimates in particular, though we did throw in basal area and canopy closure into our study as well. The rationale for our project and looking at stocking in particular was that we understand, and we've talked just about that, about the biases in photo interpretation. And stocking, I think, is probably one of the most nebulous, most difficult elements inside of those 40-plus attributes that are inside of the FRI. It has to be one of the most difficult that we ask a photo interpreter to do. If we are doing stocking by the books, we are asking that interpreter to come up with height and age and site class. We are asking them to estimate what the basal area of that stand is based on what they can see in canopy closure, calculate what that basal area is and compare it to normal Plonsky, which is a big, big ask. So we see, or believe anyway, that stocking can be subject to bias between interpreters, like we just discussed. So one interpreter might call a stand a different stocking value. We might see biases maybe between firms and therefore across our management units across the province. And as stocking comes into strategic forest management modeling and forecasts of allowable cuts, it's an important variable for us to look at and try to get correct. So we were trying to come up with methodologies, and Jilly will speak to the modeling that he did to create ways to automatically or create models to calculate stocking from the ADS 40-point cloud. We also did look at basal area and being able to estimate basal area directly from the ADS 40-point cloud, kind of the idea of cutting out the middleman. Let's get rid of stocking and try to directly estimate basal area. and our study area was on the Lakehead Management Unit. So our project team, I'm a big fan of collaboration. Many hands make light work, and two brains or two heads are better than one, especially if one of them is mine. So Arnold, Rudy, and myself were the sort of co-leads on the project. Dr. Julie Lee handled the majority of the modeling exercises for us. And Shanley Thompson also was instrumental in putting together a number of the stats for the project and writing our draft report. Not quite as bad as Dr. Webster had yesterday. We lost Jilly partway through the project to FP Innovations, but he was able to continue to work on the project. We lost Shanley Thompson partway through the project as well. She is now in, where is she, Arnold? Iqaluit or something like that? Yeah, which tells you what the working conditions are like at KBM if moving to Iqaluit in the winter. Seems like a better option than working for KBM. I've known Arnold for 20 years and I've worked at KBM for 14, so I'm allowed to make those jokes. So project management is split between us, and the photo interpretation work was also done at KBM. I co-led the project, helped with some of the field methodologies and did a fair amount of the writing and analysis. Joe Lattiser and Dave McIsaac at Green Mantle assisted us heavily in field site selection, and were important to have in the project as industry partners to keep us, I won't say we're not honest, but to keep us honest and to keep us, the project, focused on something that was going to be practical and relevant, and not let us get lost in the weeds or too high into the clouds. Most of you are probably familiar with where the Lakehead Management Unit is, sort of like Doug just indicated, well accessed, close to Thunder Bay, a really great study site for us to use. So this simple little table, in a nutshell, sort of describes what we did or what we were looking at when we're talking about a comparative analysis of stocking. We sent out field crews to assess the stocking of stands. We had those field crews also assess the basal area of the stands while they were there. And we developed models that would then predict stocking, predict basal area, and predict canopy closure. We asked our photo interpreters what the stocking of these stands were. The Lakehead was one of the first FRIs through the T1 process and didn't have stocking in the FRI, so we had to have that added in. And of course, we asked those photo interpreters to tell us what the crown closure was of those stands. You'll notice that we didn't ask the photo interpreters to tell us what the basal area of the stand was, because that's not standard operating procedure, and we didn't think that that was a fair thing to ask them. We also didn't assess canopy closure in the field. Canopy closure was, I don't want to say an add-on, but it wasn't the focus of our study, and we didn't want to spend time in the field assessing canopy closures at various points throughout the stand to try to come up with an accurate field representation of what canopy closure was. So the field methodologies looked like this. In 2015, we went out and collected what we would refer to as the model calibration or the model building data set. Oh, sorry, go back. You'll see here the forest units that we looked at. So we stratified and looked at 3 different forest types. It would have been really wonderful to look at all forest conditions, but we looked at this project as being a research project, a proof of concept kind of idea, so we didn't want to go out and sample all of the various forest types, 12, 13 different forest units, just to prove that it didn't work. That didn't seem like it was a good idea. So we stuck with 3 and kind of felt like we were bookending the problem here a little bit. We would look at a pure conifer forest unit in SB low. We would look at pure deciduous stands in pure deciduous stands with poplar deep, and we would look at a mixed wood condition as well to see whether or not our models could work in all of those conditions. Again, the bookending kind of idea. And if certain models performed better than others. So Julie will describe the different modeling approaches that we used, basically looking at ITC, as well as a different suite of models that looked at the texture of the stand. So in 2015, we went out and collected that plot data. We felt it was important to try to, as much as we could, keep apples to apples here. We're going to be comparing our results, our model results, and our field results to the photo interpreters. When a photo interpreter is looking at a stand, that he or she is looking at the entire stand, so we darn well better look at the entire stand as well when we're out in the field. Forest polygons, forest stands inside of the FRI are not homogeneous units. They have small inclusions that don't meet minimum polygon sizes. So we set out a systematic grid throughout our stands, and at each one of those points, the field crews would do prism sweeps. Within that stand, we would collect 3 heights and ages to collect the site class from which we could collect and determine stocking. In 2015, we looked at 95 different stands, 30 plus in each one of our strata. The density of plots inside of those stands varied based on stand size. The lakehead has relatively small polygon sizes to begin with, and we asked Dave McIsaac to find us some of the smaller ones, if he could, please, that were close to roads so that our crews didn't need to travel too far. So our stand sizes were relatively small, 5 hectares, maybe up to 60. We tried to keep them regular-ish in size. We didn't want to have long noodle polygons that we were asking the field crews to tromp across. So that you can see there the average sort of plot density, we were having anywhere from 2.4 to 2.9 prism sweeps per hectare. The spacing between those plots being about 56 meters on average. In 2016, so that was a 2015 work, we gave that data set to Jilly. He did some wonderful magic. And then in 2016, we went out to go test his models against a new set of stands. So in 2016, we did a very similar exercise. In this case, we learned a little bit from our 2015 work and decided that we didn't need to put in quite as many plots necessarily in all of the stands. If you do 12 prism sweeps and you're getting the same basal area 12 times, maybe you don't need to put in 30, and maybe we could move on to the next stand. So we ended up putting in more prism sweeps in the heterogeneous stands and fewer prism sweeps in the stands that seemed homogeneous when we were in the field. So that was a field calculation that our crews were doing while they were out there. The minimum number of plots per stand stayed at 12, and we capped it at 30 as a maximum. So again, you can see the plot density there of 1.5 to 2.9 plots per hectare in 2016. The field crew methodology was fairly straightforward. At each one of those plots, a prism sweep was done. We chose to use BAF4 to do this, to sort of limit the number of trees that needed to be counted and the number of limiting distance calculations that were required. 3 heights and ages were taken within the stand to calculate site class, and therefore we could determine stocking. We also asked the field crews to take photos at the height age locations for reference later on to see if something didn't jive, if their field data wasn't matching up with what we were seeing in the imagery. We could go back and look at those photos and also look at any notes that they'd collected to maybe see stand breakup or something that may have happened in the intervening years. So I'm going to turn it over to Jilly, who will walk us through the modeling methodologies.
Good morning, everyone. Before I describe the detailed methodology, there's some key component that I want to mention. When I designed this modeling approach, I was thinking, because it's kind of a proof of concept, so I'm going to make it very simple. So I'm not going to use very complex machine learning algorithms to build a very fantastic model, and I thought of going back to the traditional linear regression. And the second rule is I want to step from the digital terrain model because most of people don't really want to rely on the LiDAR data to create a digital terrain model. So is there any way that I can only use enforced forest inventory imagery to infer the stalking and the crown closure and basal area? That's the second rule. And the third rule is that I want to come up with some variables or features from the remote sensor imagery to directly describe the physical meaning of stalking and the physical meaning of crown closure or even the basal areas. And I don't want to go back to the traditional way that we build a fantastic regression model to predict the stalking from structural variables, from the soil variables, from the site index variables. That's not the focus of this model design. So here we go, we have 3 models that have been developed. The first model is individual tree crown area and density model, which is sort of modified version of my early PhD research, which I use a LiDAR. And the second model is sort of texture descriptors, trying to come up with some meaningful texture measurement from the imagery or from the point cloud that can describe the smoothness of the stand canopy, because we think that the smoothness sometimes can be related to the stalking. If the stand is more homogeneous, very smooth canopy on the top, then maybe the stalking value is a little high, opposite, vice versa. The third model is we want to see if we combine these two together, what result we can get. And separate models were created for each of the 3 forest unit Keith just mentioned. The first step is we create an ADS-40 point cloud from using the Trimble software while I was in KBM. When we created the point cloud, it's not the usual way that everyone did. We try to go up higher level to produce very, very dense point cloud. We try to bump up the computer limitations. So basically one block, we took a lot of hours to process generating the point cloud. And the point cloud density is very huge. So that's just the example of what's the point cloud and the rasterized imagery looks like. So we created a digital surface model from the point cloud, and also we created a digital terrain model from the point cloud. This digital terrain model is directly coming from the software, which is not an accurate digital terrain model. But keep in mind that in these algorithms, I don't need a very accurate digital terrain model because I don't estimate the height of the individual trees. I don't want to rely on that information. So I can say it's just a pseudo digital terrain model. Example of digital surface rasters overlaid with a plot boundary, a little bit buffer on the edge. And also we continue to create a 40 centimeter pseudo canopy height model used for texture analysis. So I use the digital surface model for my individual tree crown algorithm variables, but I use the canopy height model for the texture analysis. This is a imagery shows the polygon of individual tree crown segmentation. I use a traditional watershed segmentation, but it was built on the surface elevation model. So the pink representation on the image, it could be 400 meters, 500 meters, not the typical 10 meters height of the tree. And then from that polygon segment, I come up with histogram of the individual tree crown area statistics. So this rectangle bars showing that how the area is distributed for one plot, one stand. The X meaning the area. So the number 200, 400, this is not a correct number corresponding to the area, but some scale values that I made, which I couldn't remember clearly. So the y-axis is the power, is the density, sort of scaled frequency distribution of the crown area. And then I use a Weibull function or inverse the Gaussian function to fit the histogram, trying to get the parameters, the scaled parameters and shape parameters, and then pick up the shape parameters as a representative of my ITC model variables. It's pretty simple, just feed a line, feed a function, that's it. So get the parameters. And then I selected 7 variables from this group, such as the area per stand, the statistic of the area, how it distributes across the whole block, and the value of the shape of the model of the function that I used to fit the histogram, and the density of the stand. So we count how many trees, how many individual tree crowns within the stand, and then calculate the canopy cover of the stand, which is directly used as an estimation of crown closure. The second group is texture variable that I used. It's sort of similar as the traditional grid level concurrent analysis, but I use the median absolute difference, MAD, called. And MAD is sort of texture descriptor that can calculate measuring the difference of values when you have a window on the imagery. You move the window along the line and you calculate the difference by moving the window, the mean digital value difference. So then calculate the ratio between different legs, between different distances, and come up with the texture features. So again, 7 variables were selected by myself and in the texture group, that including some stats of digital surface model per stand, some height. It's not the real height, it's just some statistical pseudo height. Maybe the height for 20-meter tree is only 5 meters in my model, but that doesn't matter. So it's a kind of relative height, mean height. And in the end, we have the relative roughness index used to describe the ratio between different legs on the texture imagery. Okay, so he's gonna continue.
Thank God I didn't have to do that. Okay, so now we'll get to the results. So Jilly created the ITC models with his ITC variables and texture models, and as well created a combined model that could use variables from either one of those two, and we put them to the test against the photo interpreters, of which I'll get Alf's question before he has a chance to answer it. There was 4 photo interpreters, and we averaged the results together to compare. So you can argue that maybe that wasn't a statistically valid number of photo interpreters, but it was better than 1. So we looked at photo interpreters and those various models and compared them to what we found in the field. And this differs from Doug's results in the sense that we found, I'm going to sound like a broken record for both the next 6 slides, we found statistically significant differences between what we were finding in the field and what the photo interpreters were telling us stocking was in every single cover type, those 3 cover types that we looked at. So you can see here I've left out a number of the other stats that we calculated, and I'm showing you mean difference, standard error, and most importantly, the significant difference test. So you can see here that our field values for stocking are significantly higher than what the photo interpreters would tell us, and I'll speak to that in a little bit more detail on the discussion slide later on, but you're going to see this a number of times. Whereas all 3, I guess, the ITC, the texture, and the combined models were able to show no significant difference between what the field data was telling us. So quite encouraging results in that sense. Looking at basal area, again, we didn't ask the photo interpreters to tell us basal area because that's not their job on a day-to-day basis. But basal area in the field compared to our models, again, no significant difference between what what our models were able to predict from the ADS 40-point cloud and what we were seeing as basal area as recorded in the field. Those were for con mix, those last 2 slides. Looking at poplar deep, rinse and repeat, statistically significant differences between the field recorded stocking values and what our photo interpreters were recording as stocking. You'll see again our photo interpreters are underestimating stocking in comparison to what we were seeing in the field, and our texture models, ITC models, and the combined models were able to predict field stocking with no significant difference. Similar results, poplar deep, when we look at basal area. So mean differences between what we're seeing in the field and what we're seeing with the models with respect to basal area meter squared per hectare here is somewhere around 1 meter squared. S below, again, quite similar. Statistically significant difference between what the photo interpreters were telling us the stocking of these S below stands are and what we were seeing in the field. 2 of our models were able to predict with no significant difference the stocking that we saw in the field and the stocking that's presented by the models, though our texture model didn't perform quite as well in S below. And it was kind of interesting when we were looking at when we were coming up with the project idea. I kind of felt like S below was going to be the really easy one for us, and it was actually the most difficult for us to predict or get correct from the models. And again, with the results for the basal area, we see no significant difference with the ITC and the texture models when we're looking at basal area results for S below. So the histogram and the table show you those differences. So again, maybe the ability for our models to predict basal area within 1 to 2 meters squared. So thinking that this would be a wonderful addition to your forest inventory if you could have a basal area attribute automatically calculated. So I guess the take-home message here is that we saw in all 3 instances that we looked at, photo-interpreted results significantly underestimating what we were seeing in the field. And this is, we don't want to turn this into a photo interpretation bashing exercise, but if you have photo interpreted yourself or if you speak to photo interpreters, I challenge you to ask them how many times they call stocking over 1.0, and they will say 0 unless the field data tells me so. There's a heavy bias to not call stocking over 1.0, and when we were seeing these differences between our field data and the photo interpreters was in those instances where the field data is saying that we have overstocked, stocking greater than 1.0 stands. And those exist on the lakehead forest. The lakehead forest might not be running on normal yield curves. It's a heavily utilized forest and might not be following those trajectories. So we're seeing lots of stands. In our case, we had 17% of our stands that had a stocking over 1.0. Meanwhile, our photo interpreters were able to only call those stockings over 1.0 2 times. As I was looking at those results, I was kind of wondering if people were going to question whether or not maybe our photo interpreters just weren't that good. Maybe our field crews were just a little generous with their sweeps. Maybe this is a result, a discrepancy we're seeing between photo interpreters and the field data that's study specific. So to address that a little bit anyway, I looked at 3 FRIs that are in the region, the dog mat, the cross route, and the White River. I queried out just the forested polygons. How many of those forest polygons inside of your FRI have a stocking greater than 1.0? It is less than 1% of the stands. And then I looked at the field calibration plots for those FRIs. And how many of the FRI lines, the field calibration plots for those FRIs, have stocking over 1.0? And it is anywhere between 8 to 19%. So even inside of our own FRI methodologies, our field data tells us there's a number of stands out there that have stocking greater than 1.0, but we don't see that translating into our delivered FRI product through in photo interpretation. We didn't speak to this in great detail, but it's in the report if you'd love to read it. That which of these models perform better and which of the variables that Jilly created were better predictors. And we were seeing actually the texture variables performing better than the ITC as a general rule. Some of that we think may be a result of the terrain model that we're working with or lack thereof that we were working with. And again, basal area predictors seem quite strong. Sorry, I didn't speak in great deal to canopy closure, but we didn't see a great correlation between the ITC canopy closure that we're creating from the models and what we're seeing in photo interpretation. But again, we didn't have field data to determine which one was truth for us. So some of the limitations or sort of further work that we might think about here. One of the discrepancies that we might see between errors that we might see in what we were doing was the time lag between the models and the photo interpreters working with data. That was from 2008. They're looking at 2008 imagery, and we were in the field in 2015, 2016, so maybe there was some not quite apples to apples happening there. Jilly alluded to the idea that what we were doing was computationally intensive, though I'm leery to put that out as much of a limitation as we know computing technologies move quite rapidly. A significant amount of the budget was spent on going out to collect this data. So as we talk after the next presentations about how we could work together in the future, I think even looking at Doug's work, there may have been some opportunities here to collaborate on field collection and save some pennies. We're also thinking about maybe trying to ways to incorporate the FRI calibration lines to be able to create some of these models or test data sets. And always more technology is better. We were leery inside of our proposal. I think even in our first draft letter of intent, we talked about incorporating LiDAR, but we veered away from that in the project because we wanted to work with what we had, which was the ADS-40 imagery. The new ADS imagery that comes out in T2 may provide us abilities to do increased accuracies in our modeling, and certainly we're excited about the idea of having a more detailed terrain model, however that arrives. And Julie also mentioned this while he was going through his presentation, or his portion, is that we could look at methodologies that are beyond regression to create more sophisticated models. And I'd like just to acknowledge some of my colleagues at Confederation College. Thank you also, because I've been on strike for the last 3 weeks, so I haven't been in front of a classroom. I really am resisting the urge to give you a pop quiz right now. So I've got a number of colleagues at Confederation College who helped. Larry Van Dam at KPM, thanks to Dave McIsaac, he did a lot of work with us on the site selection, as well as folks at Green Forest and some of our field crews in Steve and Ashley Allen. So we can open up to questions, or we can have questions while we're having coffee or whatever we need to do.
We've got time for a couple questions.
Do we have time for a couple questions?
Hi, Keith. Great talk. Did I interpret that right? You guys used a BAF4?
Yes.
So what was behind the decision to use the BAF4 as opposed to BAF2, which is more common?
I'm not going to quote the studies from you because I don't have them off the top of my head, but I understand. I know that BAF2 is a standard operating procedure, but if you read the literature on using prisms, the ideal sort of sweet spot for the number of trees you should have inside of a suite is anywhere from 6 to 8 to 9 using a BAF2, and just counting extra trees increases time, increases the number of limiting distance calculations that you have to do. So certainly using a BAF4, we're counting fewer trees, but the field crews, again, well trained and well directed on this. Of course, using the BAF4 plus or minus a tree matters much more than using the BAF2. So it was a question, the decision to go with the 4 was an efficiency decision, and I'm sort of, again, not to question the methodologies we use in Ontario and the reasons why we use them, but I feel that the BAF4 is a more appropriate prism to actually be using here.
Okay, and the other part of it was, did you also ignore all the 10 centimeter trees?
Yes.
When you were looking at the calibration plot data for the stands that had greater than 1 stocking, did you look at the age and whether or not they tallied under 10 centimeter trees?
For our calibration data?
Yeah, you said 8 to 19% were over or greater than 1.0 stocking in the calibration plots.
Yeah, I didn't break it out in terms of the ages that would have been.
So you didn't limit it to the same forest types and ages that you restricted your plot example? Or?
Oh, when I was looking at the different FRIs?
Yeah.
No, I didn't.